So let me start recording here. Okay, so this is section 6.2, which is the Law of Sines. So basically, last class we were working on solving right triangles, right? So we had a right triangle and we were finding the missing angles and the missing sides. And so we were able to use trig to do that. And so today we want to do the same thing, but we want to find missing angles and sides of any triangle. So the goal of today is to be able to find missing angles and sides of any triangle. So it doesn't have to be a right triangle anymore, right? So since we don't have a right triangle, we can't just use, the sine is the opposite over the hypotenuse, because unless you have a right triangle, you don't have a hypotenuse, right? So we're talking about maybe I have some random triangle that looks like that, right? So we'll call this A, and we'll call this B, and we'll call this point C. Which we're still going to label the side across from capital A as little a, the side across from capital B as little b, and the side across from capital C as little c. And so the idea is I want to try to figure out some way to relate these things. So what I'm going to do for you, so the way we're going to relate them is what's called the Law of Sines. I'm going to show you where the Law of Sines comes from. So it doesn't look like I'm just plucking it out of thin air and writing it down. You do not need to be able to reproduce finding the Law of Sines. We are going to do problems where we actually use the Law of Sines. That's what you're going to have to do. And I will write down what the Law of Sines is. But this first part is just to kind of show you this is where the Law of Sines comes from. Okay. And so what we're going to do is we're actually going to put in, oops, my line does not look very straight here. We're going to put in this perpendicular line here. So we have a right triangle and that side is H. Now the way I drew my triangle, it kind of looks like that dotted line splits stuff in half. It's just the way it's drawn, so we can't assume that. But basically, we've split stuff into this blue triangle on this side and this pink triangle on this side, and both the blue and the pink triangle are right triangles. So since it's a right triangle, I actually can use trig on them. So what I could say is if I look at the pink triangle, so in the pink triangle, we can say that the sine of A, right? So remember, sine is opposite. So in this case, the opposite is that H, the height, over the hypotenuse. In this case, the hypotenuse of that pink triangle is B, right? Remember, here's my right angle. The hypotenuse is always across from the right angle. So I know the letters are a little different than we're usually used to doing, but we usually are using H for hypotenuse and B for one of the legs of the triangle. But here I've kind of changed that up a little bit. But I'm still really just using that the sine is the opposite over the hypotenuse. And then I can make a similar relationship for the blue triangle. So in the blue triangle, the sine of B is going to be the opposite side, so H, over the hypotenuse, which in the blue triangle, the hypotenuse is actually A. So I have that the sine of A is equal to H over little b, and the sine of capital B is equal to H over little a. And what I could do is I could solve each one of these for H. So in the pink side here, to solve for H, I would multiply the B up. So we would end up with B sine A equals little h. In the blue triangle, I'd multiply the A up, so I'd get A sine B equals little h. And then if both of those things are equal to little h, I can actually set them equal to each other. So these two things combine together to say B sine of capital A is equal to little a sine of capital B. And so the reason I did that is because, again, both of those things are equal to h. And then what I can do is I can kind of rearrange stuff here. I'm going to divide both sides by b. And so on this side, the b's cancel out. I'm also going to divide both sides by a. So on this side, the a's cancel out. And so what I'm left with is that the sine of a over little a is equal to the sine of b over little b. And if you notice, I got rid of h. And so the reason why it's good that I got rid of h is because h had to do with it being a right triangle, making that line in there to make h. But now I have a relationship that just relates capital A and side A and capital B and side B. And that would work for any triangle. It doesn't have to be a right triangle. And so that's actually part of the law of sines. What the law of sine says, and this is the part that you need to know. So you don't have to know all the other stuff I did here, but you need to know the law of sine. So the law of sine says for any triangle, the sine of capital A over lowercase a equals the sine of capital B over lowercase b equals the sine of capital C over lowercase c. So I know in what I just did, we didn't get the sine of capital C over lowercase c. We would have to do the same thing I did, but drop a different h, like make a different right triangle to get it. And so it's this part here, this stuff here, this law of sines, that you need to know and that we're going to use. So in any triangle, if you take the sine of an angle over the opposite side, it's going to be the same ratio as a different angle over the opposite side. Questions? No?
Yes, I have a question.
Sure.
On the right side, so why did you combine the two together to get sine capital A all over lowercase a to equal sine?
I combined them together to actually just show you where the law of sines came from. So since the law of sines here is sine of capital A over A equals sine of capital B over B, that's why over here, when I saw, I have this equals H and this equals H, so if this is the same as this, that means that this part here has to be the same as this part here. So I combine this whole entire side here is really just showing you where the law of sines comes from. So this is how like mathematicians came up with the law of sines. They noticed this stuff about triangles. But the important part for us is to actually just know the law of sines, and then we're going to use it in problems. Does that help answer your question?
Yes, so so the one on the right is what we're going to be using, and then the law of sine also what you just
No, so all this stuff in the green here, whoops, why isn't oh, there it is showing. Okay, this stuff in the green here, in this green bubble, that's the important thing. That's the only thing you need to know.
Oh, okay, got it.
And so we're going to use that. So all the other stuff on the page right here just showed where the stuff in green came from. So it's not like I could have just at the very beginning written, here's the law of sines. Boom. You just trust me because I'm your math teacher. Instead, I was like, well, here, let me show you where it comes from. And now maybe I'm a little more trustworthy because I showed you where it comes from. Okay, so let's try some examples. All right, so solve the triangles, right? So this is the same as what we were doing last class, right? We need to, when you see solve the triangles, we're trying to find all the angles and all the sides. So my first triangle here tells me that lowercase a equals 7, capital B equals 25 degrees, and capital C equals 106 degrees. So they've given me some information about the triangle, and it's not a right triangle, right? a right triangle, the biggest angle would be 90 degrees. And you can see we already have a 106 degree angle. I generally just draw a generic triangle to kind of to make a picture. It doesn't matter what your triangle looks like. It doesn't really matter what you call A, B, and C. So I'm going to do them kind of how I had it before, A, B, and C. And then I'm going to label the stuff that they told me. So they told me that side A, so remember side little a is across from capital A, so that's going to be a 7. They told me that capital B is 25 degrees and capital C is 106 degrees. So I need to find capital A. I also need to find little b and little c. So just like in the problems we were doing last class, right? I happen to know 2 angles of the triangle. And so we talked about last class, all the angles in a triangle add up to what? Yeah, 180 degrees. So that means angle A, capital A plus capital B plus capital C has to be 180 degrees. So capital A, we don't know. Capital B is 25. Capital C is 106. That has to be equal to 180. So A plus 131 has to equal 180. So A ends up being equal to 49 degrees. So now I know this here is 49 degrees. And then we are going to use the law of sines to help us find B and C. So which one do you want to find first? Do you want to find lowercase b or lowercase c? Okay. Lots of people saying different ones. Let's see. We'll take whatever one came up first. Okay, so John said B first. So we'll do lowercase b. We're going to find them both. We're going to find it the exact same way if I had done lowercase c first, so it doesn't matter which one you do first. Okay, so to use the law of sines, one of the things that you need is you need to know an angle and the side across from it. So if you look here, I happen to know angle A, and I also know the side. Oops, I didn't mean to hit that. So I happen to know angle A, and I also know the side across from angle A. So we're going to use this pairing, right? So this pairing here is going to tell us, so remember the law of sine said, the sine of A over little a equals the sine of B over little b equals the sine of C over little c. So you can use whatever pieces of this you need. So I know that the A part, so we know that the sine of 49 degrees over 7, that has to be equal to, so we're going to look for B. So since we're going to look for B, we're going to use the sine of capital B. So this would be the sine of 25 degrees over lowercase b. So basically I just set up my ratio there using the law of sines. Questions about how I set up the ratio? No? Yeah, so the law of sines does also work for right triangles. Yep, you could use the law of sines for a right triangle. So it's not, it works for any triangle. Yep. Other questions? No problem. So now I'm going to cross multiply, right? So we're going to have B sine 49 degrees equals 7 sine 25 degrees. And then I'm trying to solve for B, so I'm going to divide both sides by the sine of 49 degrees. So B is going to end up being 7 sine 25 degrees divided by the sine of 49 degrees. And you don't want to, so like sometimes people try to like figure out what those things are in the middle steps. Like they'll try to figure out, oh, what's the sine of 25 and what's the sine of 49 and put numbers there instead. You don't want to do that until the final step. You want to plug this whole thing into your calculator at the final step to figure out what this is, so we don't get any of those rounding errors. So somebody asked me, why is it over the sine of 49? So because I'm trying to get the b here by itself, right? So I had b times this stuff, so I have to divide it to get rid of it. So I'm trying to get the b by itself. So since I had b times all this stuff, we're going to divide both sides by that same stuff. So that's why it's the sine of 49. Does that make sense? Okay. And then if you plug this into your calculator, you get that b is approximately 8.9. So I know that b is about 8.9. And just like when we did the problems the other day, since I rounded b, little b there, if at all possible, I want to try to avoid using it to find c. So to find c, we're going to do the law of sines again. We're going to use, again, this sine of 49 equals 7, and then we're going to have to use this pair. Oh, no, you're right. I wrote down the wrong number. Oops. You guys are right. I wrote down. That's what C is. Sorry. 3.9. I should be a little more careful when I'm reading from my notes. Sorry about that. Yeah, it's 3.9, not 8.9. Okay. So, no, you guys were right. I was wrong. So to find C, we're going to do the same thing. So we're going to do the sine. Again, we're going to use that 49 degrees over 7. But this time we're going to deal with the stuff with C. So the sine of 106 degrees over little c. And just like before, we're going to cross multiply. So C sine 49 degrees equals 7 times the sine of 106 degrees. And then we're going to divide both sides by the sine of 49 degrees. So C is going to be 7 sine 106 degrees divided by the sine of 49 degrees, or approximately 8.9.
Can you go over really quick how you got the setup of 49 over 7?
How I got, wait, say that one more time. Let me just turn up the volume.
You got 49 degrees set up over 7, and to use the rule of sine, right?
Yeah, so I'm using the law of sines, right? But in this case, I'm basically, when you do the law of sines, you can pick any of the two pieces you want. So I'm using the sine of A over A and the sine of C over C. So in terms of my picture here, the sine A is 49, so the sine of 49 degrees over the side opposite it, so over 7. And then C, so capital C is 106, so the sine of 106 over lowercase c. So it's always, the law of sines is always taking an angle and the side opposite it. So angle over the side, sine of the angle over the side.
Okay, I see.
Other questions? No. Okay, so if you're given two angles, the law of sines is easy. If you're not given two angles, it's not that the law of sines is hard, it's just that you kind of have a couple options of things that could happen. So, does anybody need me to wait before I go to the next slide and do our next example? Sure, not a problem. Just let me know when you're ready for me to go on. Okay, so let's try another one here. So little c is equal to 40, little b is equal to 63, and capital C is equal to, 28 degrees. So again, right, I'm just going to draw some random triangle. I personally don't even care if my triangle is drawn to scale, right? So I generally tend to keep labeling my triangle the same way, ABC. So in this case, right, angle C is 28 degrees. This angle here looks bigger than 28 degrees. That's okay. I personally just draw the triangle so I can see, what is opposite each other. That's the only reason I draw the triangle. Little b is going to be opposite capital B, so that's 63. And little c is going to be opposite capital C, so that's 40. So in this case, unlike the last problem, I can't first there's not only one angle missing, there's two angles missing, right? But I happen to already have one pair, right? So I happen to have that the sine of C, or I happen to have the angle C and the side C. So I can set up using the law of sines. Remember, the law of sines, you need an angle and a side. So in our case, we're going to have that the sine of 28 degrees over 40. And then we need to pick we either need to use A or we need to use B. And I should have labeled this here as little a. I'm going to pick B. The reason I'm not going to pick A is because I don't know angle A and I also don't know side A. So I'd be making an equation with two things I don't know. At least in the B, I happen to know the side. So this is going to be equal to the sine of angle B, which I don't know, divided by the side, which is 63. So if I cross multiply, right? So I need to figure out what capital B is. So I'm going to cross multiply. Or I don't even have to cross multiply. I just need to move the 63 up, right, to get the sine of B by itself. So 63 times the sine of 28 degrees over 40 is going to be equal to the sine of B. And then we did do some problems like this last class, right, where we're looking for the angle. So I'm looking for the sine of B. And I have what the sine of B is, and I'm trying to figure out what B is. So does anybody remember from the last class what we did to untrap the B to get the B by itself? Yeah, we did the inverse sine. So essentially what I'm doing is I'm taking the inverse sine of this side and the inverse sine of this side. So on the left side, we have the inverse sine of I can write this a little cleaner. 63 sine 28 degrees, all divided by 40. And then on the right-hand side, that's just going to turn out to be equal to B. And I'm going to save myself a little bit of room, so I'm actually going to kind of put this up here. So if you work this out, B turns out to be approximately 47.7 degrees. So, questions so far on anything I did? You could cross multiply, but if you cross multiply, you're going to come to the exact same point I'm at, and you're still going to have to, like, I'll draw it down here, but I'm going to erase it because I'm going to need this room down here to do other stuff. But had you cross multiplied, you would have gotten 63 sine 28 degrees equals 40 sine B. And again, you're trying to get the B by itself, so you would need to divide both sides by 40. And then you're at the exact same place I was, which was the sine of B is equal to 63 sine 28 degrees divided by 40. And so you still have to, the B is attached to the sine function, right? Remember, I can't separate them. It's not like sine is one thing and B is something different. It's the sine of B. The two are attached. And the only way to undo the sine is by using the inverse. Does that help explain that? Other questions? Are you asking why didn't I, like at the beginning, why didn't I cross multiply to get 40 to both sides? Or what are you asking, why did I pick to multiply both sides by 63? I just want to make sure I'm answering the right question. You could have cross multiplied at the beginning. That's what I did here, right? So I came down here and I said, all right, well, you could cross multiply and get 63 sine 28 equals 40 sine B. But then you're trying to solve for B. So eventually you're going to have to divide by the 40. So at the beginning here, I was like, I'm trying to get the B alone. So if I just multiply both sides by 63, then I've isolated the part with the B. That's why I multiplied the 63 up instead of doing cross multiplying at the beginning. But you could have done cross multiplying at the beginning. You would get to the exact same space. That's what I did down here. Other questions? Okay. When you use the law of sines to get an angle, right? Because we use the inverse. Remember when we did inverse functions, the inverse sine, we only define it in quadrant 1 and quadrant 4, right? All of our triangles, we're going to be getting values in quadrant 1 because we're dealing with positive angles. But remember, on the unit circle, right? If you remember, I don't have a great place to do this, but if you remember on the unit circle, remember the sine is positive in the first quadrant or the second quadrant. When we do the inverse sine, we only get answers here in the first quadrant. Because I use the inverse sine here to find B, I have to actually check to see if there's another B over here in quadrant 2. Okay. So when you use so people like the law of sines because it's like easy to remember. The algebra is not that hard compared to next class. We're going to learn the law of cosines. People like the law of sines. However, when you do the law of sines, if you use the law of sines to find an angle, like we just did, you also have to check for the angle that's in quadrant 2. So B could end up being 47.7, or B could be in quadrant 2, and in quadrant 2 it would be 180 minus the 47.7 degrees. So B could also be, in this case, 132.3 degrees. So when you do the law of sines and you find an angle, you potentially get 2 different cases you have to do. So let me erase all this kind of extra stuff here. So this is just an unfortunate consequence of the law of sines. And so what it means is that now, so inverse sine is in quadrant 1 and quadrant 4. But the reason we restrict to quadrant 1 and quadrant 4 is because quadrant 2 and quadrant 3, they repeat. So quadrant 1 and quadrant 2 mirror each other. The values in quadrant 1 for sine and quadrant 2 for sine are the same. Quadrant 3 and quadrant 4 in terms of sine are the same. So when we're doing the inverse function, we restrict to just quadrants 1 and 4. But really here, we're solving an equation. And remember, when we solved the equation, we had to look at the whole unit circle. So when we're solving this, because we solved from the equation, we have to look at the whole unit circle, which means we have to look in quadrant 1 and quadrant 2. And it's because we use the inverse sine. The inverse sine is only ever going to give us one answer, but there's potentially two answers. No problem. So we are going to have two different cases that we have to look at. So case 1, we're going to look at B being equal to 47.7 degrees. Case 2, we're going to look at B being equal to 132.3 degrees. Right? So we actually are going to potentially get two answers here. So I personally... Go ahead.
Sorry, I think I missed something. How did you get 132.3 degrees?
So I got it by taking 180, right, minus 47.7. So basically, to get the angle, the corresponding angle in quadrant 2, if you think about it, when you go all the way around the top half of the unit circle, that's 180 degrees. So we're doing, to find the angle in quadrant 2, we're doing 180 degrees minus the angle that we had in quadrant 1. So that's what's going to give us the angle in quadrant 2. So it's always going to be, to get the angle in quadrant 2, it's always going to be 180 minus our answer, minus the answer we just got. So 180 minus the 47.7.
Okay, thank you.
No problem. Other questions? Okay, so I like to redraw my triangle here, just so I kind of have a triangle with what I'm working with. So right now we have 47.7 degrees in here. We have 28 degrees in here. This is 63. This is 40. This is little a. Capital C, capital B, capital A. So now in this little triangle here, I know two of the angles, right? I know 28 and 47.7. So the first thing I'm going to do is I'm going to find capital A, right? So capital A plus capital B plus capital C has to be 180 degrees because I have a triangle. Capital A is what I don't know. So capital A plus 28 degrees plus 47.7 degrees equals 180 degrees. I just want to save room so we kind of can keep everything on one page here. So doing that, I'm going to write down what A equals, but I'm confident that like you guys can fill in the steps in between here. Oops, I'm looking at the wrong. Don't write 83.5. That's definitely wrong. It is 104.3. So in this case, right, to find capital A, I had to use lowercase b. I had to use capital B, but remember, capital B here is the one I found. So I only want to use capital B if I absolutely have to, right? So I absolutely have to use capital B to find capital A. But to find lowercase a, I do not need to use capital B. So I am going to use, I have this pair, the 28 degrees and the 40. So we're going to do the sine of 28 over 40 equals, now we're going to use this pair, But in this case, I now know that A is a 104.3. So it's equal to the sine of 104.3 degrees over lowercase a. So cross multiply. A sine 28 degrees equals 40 sine 104.3 degrees. Divide both sides by the sine of 28 degrees. A is going to turn out to be roughly equal to 82.6. So that's one of my answers, right? So one of my answers is capital B is 47.7, capital A is 104.3, lowercase a is 82.6, right? Those were the three things that were missing in the original problem, and so I found them. So that's one of my answers. Then we're going to do the same thing, but using capital B being 132.3 degrees. Questions? Okay, so again, I'm going to draw myself a little new triangle, right? In this case, B 132.3 degrees. C is still 28 degrees. A, I still don't know. Little a, 63, 40, capital B, capital C. Just like before, right? Capital A plus capital B plus capital C is going to be 180 degrees. So capital A plus 132.3 degrees plus 28 degrees equals 180 degrees. And again, if you solve for capital A, you end up with 19.7 degrees. And then, just like before, we're going to use the law of sines. So again, the sine of 28 degrees over 40 is going to be equal to the sine of 19.7 degrees over little lowercase a. Just like before, cross multiply. A sine 28 degrees equals 40 sine 19.7 degrees. Divide both sides by the sine of 28 degrees. So A, if you work this out, is 28.7. So in this case, you get two answers, right? You get in the second case, capital B is 132.3 degrees, capital A is 19.7 degrees, and lowercase a is 28.7 degrees. Questions? So it's a little weird, right? It's just when you use the law of sines and you end up using that inverse sine, you're going to get two answers, or two things you have to consider. I figure people probably need me to wait a minute before I go to the next page, because I know that's a lot of writing. So yeah, so this is like the one quirk of the law of sines. And you'll see, as I kind of said, next class when we do the law of cosines, the law of cosines doesn't have this quirk in it, but then okay, yeah, so by looking at it, you have the potential for two answers if you're only given one angle to start with, So at the beginning here, we were only given one angle. We were only given the 28 degrees. We weren't given any other angle. And so if I have two angles that are missing, then that's going to lead to the potential that you could get two different answers. Does that help? No problem. Does anybody need me to still wait before I go on to the next page? No? Okay. Oops. Okay, so let's try another one. So C, B equals 5, C equals 12, and capital C equals 73 degrees. So again, looking at this, right, I have only one angle, the capital C, so I know I'm going to be in that case where I'm going to have two cases I have to look at. So again, if I look at A, B, C, capital C, 73 degrees, lowercase b is 5, lowercase c is 12, this side here is lowercase a. So again, I'm going to start off by trying to find one of the angles. So I have the one matching pair here, capital C, and then side C. So we're going to have that the sine of 73 degrees over 12. And then if I look, the side I currently have, I have the 5 that is across from the B. So I'm going to use the sine of capital B over 5. And again, I need to find B, right? So you could cross multiply. I'm just going to multiply the 5 up because I want to isolate the part that has the B. So 5 times the sine of 73 degrees over 12 is going to be equal to the sine of B. And then to untrap it, we're going to use the inverse sign. So the inverse sign of 5 sine 73 degrees divided by 12. And if you work that out, capital B ends up being equal to 23.5 degrees. And again, I used an inverse sign to get that B. So I also have to look at, or I have to look at the one that's in quadrant 2, which is going to be 180 minus what we just found, so minus 23.5 degrees, or 156.5 degrees. And so just like before, we have two cases, right? So case 1, B equals 23.5 degrees. Case 2, B equals 156.5 degrees. Questions so far? Sure. Let me know when you're ready. I should say these problems, you definitely want to use a calculator, right? You're not going to be able to do these problems without a calculator. Alex, when you're doing the homework, does have a calculator for these problems, right? So you can use the Alex calculator, or you can use your own calculator. So. And you might be able to gauge now why the problems from chapter 6, right? This is why I don't do the test for chapter 6 like live during class. I'll put it up and you guys will have a week to do the test. Kind of just like, an extra homework assignment that week. So that this way, you can look at your notes, you can look at examples to work the problems out. You're going to have to, use your calculator and stuff like that. So that's why. Okay, so just like I did before, I'm going to draw a triangle, right? So I'm going to draw my case 1 triangle. So in case 1, B is 23.5 degrees. C is still 73 degrees. This side's still 12. This side's still 5. We have lowercase a, capital A, C, B. So just like before, now I know 2 of the angles in the triangle. So I can, since all the angles in the triangle add up to 180 degrees, I can find what capital A is. So capital A plus 23.5 degrees plus 73 degrees is going to be 180 degrees. And if you solve that, capital A should work out to be 83.5 degrees. Oh, I see that. Thank you. Let me to recording too. Okay, so now that I know that A is the 83.5, I can use the law of sines to find little a, right? So, So the sine of, and I should really actually write higher so I have enough room. So the sine of 73 degrees over 12 is going to be equal to the sine of 83.5 degrees over little a. Again, cross multiply. So a sine 73 degrees is going to be equal to 12 times the sine of 83.5 degrees. And then we're going to divide both sides by the sine of 73 degrees. And if you do that, A should turn out to be 12.5. So questions on that side, on the case 1 side. No. Okay, let's see. I saw on the last problem we used B. Wait, like, you mean like the previous problem, like part B, I used the sine of B over B? So I use the sine of B over B here, right? Because I was given 63 and that's across from B. It doesn't matter what you use as long as you use an angle and the side across from it. So same thing here. I knew 5, so across from the 5 is capital B. So I did use capital B over lowercase b here. But then down here, I'm using this pair, the 73 and the 12, because I know none of those are rounded. That's why I'm not using the 23.5 and the 5, because the 23.5 and the 5 are rounded. You technically could use them. It's just that since we already rounded once to get the 23.5, potentially you're going to create like a bigger error. So that's why I try to stick with using the ones that I know don't come from being rounded. Okay, so in B, right, again, if I draw the triangle, right, so here's capital B, capital A, capital C. Now B is 156.5 degrees, capital C is 73 degrees. Again, this is 12, this is A, this is 5. Okay, so again, I have to find capital A first. So capital A plus capital B plus capital C equals 180 degrees. So capital A plus capital B, 156.5 degrees, plus capital C, 73 degrees, equals 180 degrees. And in this case, if you find capital A turns out to be negative 49.5 degrees. So, can a triangle, right, an actual physical triangle, like triangle that I draw, can it have a negative angle in it? Yeah, nope. So, case B, right, there's no triangle for case B. We don't get anything from case B. So in this case, we only get one answer. It only comes from case 1. Case 2 doesn't give us any answers. So that can happen. Like, you can break it into 2 cases, and it's possible that one of the 2 cases may not work. It's possible both cases might work, like in my last example, but it's also possible one of those 2 cases may not work, like in this example. Questions? No? Okay, so I have a couple more examples. Well, I should say I have one more example, and then I have 2 word problem examples that use the law of sines. So I think we'll probably make it through all of them today. If not, we'll finish any of them that we don't finish today on Monday. Does anybody need me to wait before I go to the next page? No? Okay. So D, little b equals 6, little c equals 12, capital B equals 38 degrees. So again, if I draw my generic triangle, right, A, B, C, 38 degrees for capital B, little b is 6, little c is 12, we need little a. So in this case, the starting pair that I happen to know is the 38 degrees and the 6, right? That's the angle on the side across from it that I know. So the sine of 38 degrees over 6 is equal to, the 12 is the only other thing I know. So we're going to say the sine of C over 12. Right? So I'm basically using the information they originally gave me in the problem. So just like before, the last 2 we found B first. This time it's a C. I'm going to multiply the 12 up. So 12 sine 38 degrees over 6 equals the sine of C. And then we take the inverse sine, right? So I'm going to leave a little bit of room because something's going to happen on this problem. So the inverse sine, I guess I don't really actually need to leave any room. So the inverse sine of 12 sine 38 degrees divided by 6. That's going to be equal to C. So if you take that and you punch that into your calculator is going to yell at you. It's going to say, like, domain error, restriction, like, can't do it. It's going to say something. And so what's actually going on is that if you were to calculate out this inside stuff here, this inside stuff is roughly about 1.23. And remember, the values of the sine function are always sitting between 1 and minus 1. So I cannot take the inverse sine of something that's bigger than 1. So what that means is there's no solution to this problem, right? They gave me like lengths, but there's no way I can actually make a triangle where where this stuff happens, right? I can't have the 38-degree angle here touching the side of 12 and have this side over here be a 6. It's just not physically possible to make a triangle that way, right? So this actually has no solution, right? So there's no triangle. Questions? Okay, so it is possible you get a problem, and that problem has no solution from the beginning. Does anybody need me? There's no inverse sine bigger than 1, or there's no sine bigger than 1. The value of sine, the sine of some number, the value of the sine of some number is never bigger than 1. So you cannot take the inverse sine of something that's bigger than 1. Does that help make it clear? No problem. Other questions? Okay. So then all right. So Ravi and Kala are standing. We're going to do this again and be slow. Riverbank, 240 meters apart. They want to know the distance from Ravi to a house located across the river. Ravi's angle to the house is 45 degrees, while Kala's is 66 degrees. What is the distance from Ravi to the house? I feel like, I think I said this last time, right? The worst thing about doing word problems online is all the writing of the problem. So if we draw a picture, right? So we'll say this point here is Ravi and this point here is Kala. And so they say they're standing on a riverbank, they're 240 meters apart. So this right here is 240 meters. And it says there's some house located across the river. So maybe the house is here. And it says that the angle from Ravi's angle to the house, so here we are, is 45 degrees. While Kala's angle to the house is 66 degrees. And we want to know what is the distance from Ravi to the house. So if we call the house capital H, right? So I have a capital R, a capital H, and a capital K. So we could label this side here. This would be lowercase k. This would be lowercase r. Right? Kind of just keeping with the idea that we'll make angles capital letters and sides lowercase letters. So we're really trying to find lowercase k, right? So I want to use, I have 66 and lowercase k, so we're going to use this for one of our pairs. The only side length I know is the 240, so I want to use the 240 for my other pair. So across from the 240 is this angle here, and I don't know what that angle is, but since I know these two angles in the triangle, it's easy enough to figure out what angle H is. So that's the first thing I'm going to do. So angle R plus angle K plus angle H, they're all in a triangle, so they're going to be 180 degrees. So 45 degrees plus 66 degrees plus H is going to be 180 degrees, or H is going to end up being equal to 69 degrees. So this angle in here is 69 degrees. And so now I know one pair, I know the 240 and the 69, and I can use that to use the law of sines to find k, which is what we're looking for. So the sine of 69 degrees over 240 has to be equal to the sine of 66 degrees over k. And if I cross multiply, k sine 69 degrees equals 240 sine 66 degrees. Divide both sides by the sine of 69 degrees. And k ends up being approximately 234.8 meters. Questions? No. Okay, so, we only have 9 minutes left in class, and 9 minutes is more than enough time to do the problem, but I don't think 9 minutes is, more than enough time to write the problem and then be able to have time to explain the problem. So why don't we stop here? I'll do this last example, next class. We'll start that before we do the law of cosines. Because the law of cosine problems actually are they're a little shorter because they're not as involved as the law of sine problems. So we'll kind of stop there for the day. But if anyone has any questions, you can feel free to ask. Otherwise, have a good weekend, and I'll see you guys all on Monday.